Class, welcome back to thermodynamics. In today's lecture, we're going to keep going with our investigation of the second law, and we're going to begin by discussing directionality. So the direction that a process takes place in thermodynamically, it leads to an increase in entropy production for an isolated system. So looking at the increase of entropy principle, this is an alternate statement of the second law of thermodynamics, okay, which states that, remember, entropy not be, can only be created. It can't be destroyed, and so entropy in an isolated system increases. So for an isolated system, remember, entropy increases. So delta S, so the change in entropy, and I'm just going to say this is isolated, is going to be equal to the integral from the first initial to the final state of del Q over T plus sigma isolated. So remember that for an isolated system, you're not getting heat transfer between the system and the surroundings. So there's no heat transfer across this boundary. So that's going to be 0. So the change in entropy in an isolated system is equal to sigma, which is the entropy production. So this is entropy production, or the total entropy produced. And so a brief note here that if we look at sigma isolated, well, that is also equal to delta S for the system plus delta S for the surroundings, where delta S isolated is equal to delta S for the system plus delta S for the surroundings. And what this really means is that in an isolated system, you can also, depending on where you delineate your boundary, you can define an isolated system as the system plus the small little envelope of surroundings that the system still interacts with, or still that the system still influences. And so note that the sum of the changes here in entropy are positive in this case. So we're still getting entropy production. And that doesn't mean that both the change in entropy for the system and the surroundings have to be positive. It means that the net delta S has to be positive. So the system could lose some entropy to its surroundings or vice versa, but overall, wherever you define this isolated system, then you're going to always have entropy production, so positive change in entropy. And also, let me add a little page here. Let's think about equilibrium. So entropy reaches its maximum at equilibrium. So as a system approaches equilibrium, entropy is going to continue to increase. And the closer you get to equilibrium, the greater entropy becomes. And so this is all we're really going to mention as far as the microscopic scale here, because in this class we're more focused on the macroscopic scale, and we're not really going to get into statistical thermodynamics, which looks at configurations of particles and energy levels on the microscopic scale. But just note that as a system moves toward equilibrium, the microscopic disorder increases, right? So when you're getting an increase in entropy, you're getting an increase in disorder. So you're getting an increase in the possible number of microscopic configurations of your particles. And so the greater entropy becomes as you head toward equilibrium, the more uncertain you become of exactly what state those particles in, like their position, their velocity. You become less certain on what those particles are doing. And I like the example that your textbook gives, that if you think about having a box with a partition in it, and we have some particles, and we're not changing the number of particles or anything like that, but there's 100% probability that these particles their location is on the right side of the box because there's a divider there. But then what happens if you remove the divider, right? And so when you remove the divider, now the volume of the box, or the volume of that the particles can be in, has doubled. And so the thing here is the particles are now going to disperse throughout the entire volume of this box, since there's no more partition, and they're going to approach equilibrium. So they're going to fill up the whole box. And so even if you have the same number of particles, now you are less certain of the position of these particles. So before you knew that they were at least on the right half of the box, but now the volume has doubled, and so you're less certain of their position, of their velocity. Entropy has increased. All right, so our knowledge of the individual particles making up the system has decreased, right? So now I'd like to move on and look at a couple of exercises from the text with you. And the first one is number 6.72 from your book. And it reads, an isolated system of total mass M is formed by mixing two equal masses of the same liquid, initially at temperatures T1 and T2. Eventually, the system attains an equilibrium state. Each mass is incompressible with constant specific heat, C. So first, we want to show that the amount of entropy produced is the following. So remember, entropy production is sigma, and that equals mc times the natural log of T1 plus T2 over 2 times T1, T2 to the 1/2. Okay, so our first task here is to show that sigma is equal to mc times the natural log of T1 plus T2 over 2 times the square root of T1, T2 for this case. And then our second task is to demonstrate that the entropy production, the sigma, must be positive. So first, let's start by just sketching out a diagram of our scenario here. And so let's say that we have an isolated system and there's some divider. So I'm just gonna, so this is well insulated. So I'm gonna draw my little insulation here. And we have two incompressible masses on each side of this box here. And the total mass is m. So if this is incompressible, we're dealing with a liquid, some incompressible liquid. Okay, so we're given that we have an incompressible liquid. So it's the same liquid at least. And I'm just going to use 1 for the left side and 2 for the right side. So we know that the left side's initially at T1, some initial temperature there, and the right side's initially at some temperature T2. And we know that the masses are equal and the total mass is m. So if the masses are equal and the total mass is m, then over here our mass is going to be m over 2. And on the right side, our mass is also going to be m over 2. And we know that we have constant specific heat C. So this is going to be initial. This is our initial condition. And now let's look at the final state. So let's remove the boundary, separating the right from the left. We're still well insulated since we're isolated. There's no heat exchange between the system and the surroundings. So still the same liquid, but now we're at some T final. And our mass is just going to be m, mass total. And this is going to be our final state. All right. And so let's start by trying to define T final. So let's look at T final. So a good place to start, so now that we're over halfway through the course, we're using both the first and second law of thermodynamics. So the first law of thermodynamics, that mass and energy can neither be created nor destroyed, well, really energy can neither be created nor destroyed, is a great place to start. And so we're going to start with our energy balance, and we can neglect kinetic and potential energy in this case. And so you end up with delta U is equal to Q minus W. Okay, things we know. Well, we're not changing the total volume of the box. We're not doing any kind of pressure work. We have no work going in. We have no work going out. We're in an isolated system, so we have no exchange of Q. So Q and W are both 0, which means that delta U is 0. And the reason why to look for the final temperature, we're beginning with an investigation of delta U, is if you remember a couple lectures ago, we were looking a little deeper at incompressible substances. And the incompressible substance model is really the key to this problem. And so with incompressible substances, recall that U the internal energy can be approximated just by the temperature. So it's only a function of temperature. And so we know that this delta U is a function of temperature, so that can bring us more information about the temperature. And so now we can say that, well, the mass, the final mass, which is mass total, which is just M, times specific internal energy, this little u, which is a function of the final temperature. So we're going to look, so delta U is, remember, U final minus U initial. So here's our U final. And let's subtract off U initial. So U initial is going to be M over 2 times U of T1, so this left side of the box, plus M over 2 U of T2. Okay, so what we're really doing is we're looking at each side of the box here. So we're doing, so because we have to look at the total in the initial conditions, okay, because we're looking at a constant mass problem here. And so in this case, this is going to equal 0 because delta U is 0. And so this tells us then that let us distribute M over 2 times C. So remember, with the incompressible substance model, actually, let's not do this part yet. M over 2, let's just distribute times U of TF minus U of T1 plus M over 2 U of TF minus U of T2 is equal to 0. So you could also think of this problem by looking at each side of the box. So the left side of the box is going to come to some equilibrium final temperature, TF. And so if you were just looking at delta U on the left side of the box, it would be half the mass times the internal energy at the final temperature minus the internal energy at the initial temperature, T1. Okay, now let's look at the right side of the box. Same thing, it's M over 2, that's half the mass, and we're going to reach some final temperature where the final temperature is an equilibrium temperature, so it's going to be the same on both sides of the box, minus U at T2. And so we can go ahead and say, well, these sides are going to be equal. Okay, and so let me add a page. Now let's build in the incompressible model. Okay, we're dealing with an incompressible liquid. And we're given that our specific heat, C, is constant. So that means that we can actually, we don't need the tables at all for U. We can calculate U, so the specific internal energy, or actually, let's do the total internal energy is going to be equal to mCT. Okay, so now let's sub this in to our expression that we've been working with. So we can say that M over 2 times C times TF minus T1. So this will give us the delta U on the left side of the box plus M over 2 C TF minus T2. So that gives us the delta U on the right side of the box is equal to 0. Okay, so now let's distribute and do some simplification. Well, if we divide both sides of this equation by MC over 2, well, 0 divided by MC over 2 is 0, so those go away. And we end up with TF minus T1 plus TF minus T2 is equal to 0. So we have 2TF minus T1 minus T2 is equal to 0. So 2TF is equal to T1 plus T2. And so we know that TF is equal to T1 plus T2 over 2. All right, so let's put a pin in that. We'll come back to that momentarily. But now we have gone through the first law of thermodynamics. We have done our energy balance. Now let's go ahead and apply the second law of thermodynamics and conduct our entropy balance. Okay, and now the key here is we were given that this is an isolated system. So as we looked at earlier in this lecture, delta S is equal to the integral from the initial to the final state of del Q over T across the boundary plus entropy produced. Well, we know that del Q over T is going to be 0, okay, because we're in an isolated system. So delta S is equal to sigma. And so delta S is equal to sigma, which is going to be equal to, well, it's going to be equal to our final minus our initial entropy. So it's going to be our total mass times our final entropy. So that'll give us total entropy final minus the initial, which is just going to be m over 2 times S1 plus m over 2 times S2. And of course, we can also write this as, actually, I'll write it out so you can see it. So we can also write this out as sigma is equal to m over 2 final entropy minus left side S1 plus final entropy minus the right side S2. Now, we're going to incorporate equation 6.13 from the textbook, which is for the incompressible substance model. And it tells us that delta S for an incompressible substance is equal to C times the natural log of T2 over T1. And remember, our T's are going to be absolute temperatures, so in this case in Kelvin. And so sigma then is going to equal m over 2. And so we're going to plug C ln T2 over T1 in for S. So we have m over 2 times C times the natural log of T final minus T initial on the left side plus the natural log of T final over T initial on the right side. Okay, so that's our delta S, C times the natural log of TF over T1 and C times the natural log of TF over T2. So that's delta S on the left side and delta S on the right side. And so now our goal was to show that this statement is correct for the entropy production. So now we have to do a little mathematical massaging here. So what we're going to do is let's combine and use the rule of addition for natural logs to do some simplification here. So this is going to equal m over 2 times C times the natural log. Okay, and so adding two natural logs is the same as multiplying within 1. So it's going to be TF times TF in the numerator, which is TF squared. And subtracting two natural logs, remember, is the same as dividing within 1. And so then it's going to be T1 times T2 together down here. Okay, so dividing by T2. Okay, now we're going to do a bit more simplification. And so we have this 1/2 on the outside, and if we wanted to put it inside our natural log, that would be the same thing as taking the square root. So raising to the power of 1/2 inside a natural log. And so this becomes MC times the natural log of, so now we take the square root of everything in the natural log to get rid of the 1/2 coefficient. And so it's going to be the square root of TF squared, which is just TF. Okay, and then we're going to have the square root of T1, T2 in the denominator, which becomes T1, T2 to the 1/2. All right, and now remember that pin we put in our TF? Well, let's take it out and use this. So we had that TF was equal to T1 plus T2 over 2. All right, so now this is going to be equal to MC times the natural log. And then for TF, we're going to insert T1 plus T2 over 2. So this is going to be T1 plus T2. And then we're going to divide by 2 times T1, T2 to the 1/2. Done. All right. So now you have an expression for entropy production if you have, for an incompressible substance of one certain liquid covering, and we're going to look at each half of a box, and this is according to temperature. And the thing here is that why would we want to express it this way? Well, it gets a little hairy when you have T1, T2, TF, so this is based just on the temperatures on each half of the box, and it gives us the total entropy production. Now our task is to demonstrate that this total entropy production is in fact positive, right? Which is, the second law says it must be in an isolated system. So let's verify that. Okay, and this is part B. So we want to show, let's look at sigma greater than or equal to 0. Okay, let's look at the cases for that. So we're going to look at it when, then. So we're going to plug in our expression then for entropy production. So MC times the natural log of T1 plus T2 over 2 T1 T2 to the 1/2 is greater than or equal to 0. So now let's get rid of this natural log. So we're going to raise E to each side, or E. Yeah, we're going to have E raised to each side. There we go. So let's see. E to the 0 is 1. We'll get rid of the natural log here. And oh, actually, first we can divide both sides by MC. Okay, so 0 divided by MC is 0. And so then we get T1 plus T2 over 2 T1 T2 to the 1/2 is greater than or equal to 1, because E to the 0 is 1. All right, so another way we can express this is that T1 plus T2 is greater than or equal to 2 T1 T2 to the 1/2. Okay, get rid of the denominator. Okay, And so let's get rid of the square root here. So let's square both sides. So we'll get T1 plus T2 squared is greater than or equal to 4 T1 T2. Okay, so we squared both sides. And now let's expand the left-hand side, and we end up with T2, or T1 squared, plus 2 T1 T2 plus T2 squared is greater than or equal to 4 T1 T2. Well, let's subtract 4 T1 T2 from both sides, and we end up with T1 squared plus, or minus now, since we're subtracting 4 T1 T2 from both sides, 2 T1 T2 plus T2 squared is greater than or equal to 0. So you might have recognized that now we can take this expression is going to be equal to T1 minus T2 squared. And that's going to be greater than or equal to 0. Whew. Okay, now let's look at this for a little bit. So what this is saying is, because we're squaring the difference between T1 and T2, that's saying that entropy production is always going to be positive unless, okay, so we know that here sigma is always going to be positive. Entropy production is always positive because we're squaring, unless T1 equals T2, and then entropy production is 0. So yes, we have verified that it will be positive as long as the two temperatures are different. All right, now let's go through one more exercise together with the remainder of this lecture and continue to look at this case with an insulated box. So in this case, this is number 6.64 from your textbook. An insulated box is initially divided into halves by a frictionless, thermally conducting piston. On one side of the piston is 1.5 cubic meters of air at 400 Kelvin and 4 bar. On the other side is 1.5 meters cubed of air at 400 Kelvin and 2 bar. The piston is released and equilibrium is attained, with the piston experiencing no change of state. Employing the ideal gas model for air, determine the final temperature in Kelvin, the final pressure in bar, and the amount of entropy produced in kilojoules per kilogram. So let's sketch out our system here. All right, so we have a box and we have a piston dividing the box equally in half. Let's pretend that this is equal. All right, so this is our piston. And the piston is not experiencing any change of state, which means we can ignore delta S for the piston. We can ignore delta U for the piston. So it just makes it our model much more easy to analyze. And the box is insulated. So I'm going to draw my insulation here. So that means it's not exchanging Q between the system and the surroundings. Now, this thermally conducting piston means that, Q could be freely exchanged from one side to the other side, and also that this piston's going to be in thermal equilibrium with the two sides. So, looking here, we have air on both sides. And the volume is the same on each side, so V1 is 1.5 cubic meters. I'm actually write it below since I don't have enough room in there. And V2 is also 1.5 cubic meters. The initial temperature is 400 Kelvin. And on the left side is 400 Kelvin and on the right side is 400 Kelvin. However, pressure on the left side is 4 bar, and pressure on the right side is 2 bar. So we're allowing this piston to move and for the system to equilibrate. So nothing is happening as far as temperature is concerned. So you can just look at here and know that because the temperature on the left side is equal to the temperature on the right side, the temperature of the piston is also going to be 400 Kelvin, and the final temperature within the system is going to be 400 Kelvin. The temperature is not changing. So we already can intuit the answer to A, but we're going to go through and solve it just to verify, but we can physically think about what's going on here and get a sense of what our answer should be. So we know what the final temperature is going to be. The final pressure, we can also kind of intuit. So in this case, the piston is dividing this box equally in half. And so we know that if what's going to happen is that, well, one side of the box is at higher pressure than the other side of the box. The left side of the box is at higher pressure than the right side of the box. And so what's going to happen is the piston is going to be pushed toward the right side of the box until an equilibrium pressure is achieved, and then it's not going to move any longer. So we can intuit actually what the final pressure is going to be just by looking at this. It's just going to be the average pressure between the two since they're divided equally. So we know that the final pressure is going to be 3 bar. Once again, we'll go through the problem and we'll show it. All right, and then it'll take a little more work to get at the entropy produced. So let's get started with part A, the final temperature. And to do that, let's begin with an energy balance. So once again, no kinetic, no potential energy effects here. So Q minus W is going to equal delta U. All right, well, what is delta U a function of? Well, for now, we're dealing with an ideal gas. And so for an ideal gas, delta U is a function of temperature. And in this case, well, the temperature on each side of the box are equal. The final temperature, delta U is going to be 0. We have no difference in temperature. So this is going to be equal to 0. And delta U is defined as M1 plus M2 in this case. So this is going to be our final minus our initial internal energy. So we have to take the total mass of the air, okay, times the internal energy, which is a function of our final temperature, minus our total mass, so for each side added together, times U for our initial temperature. And the reason I could just write this out once is because the temperature is the same on both sides. If the temperature were different on each side, it would be M1 times UT1 plus M2 times UT2. But that's not the case here. And so it's clear that T initial is equal to T final, which is going to be 400 Kelvin. Okay, so we intuited this, we showed it mathematically, and now let's move on to part B. So for part B, we want the final pressure. So the final pressure, the thing that's key here is that we're dealing with air, and air in this problem is modeled as an ideal gas. So let's look at the ideal gas law. So the final pressure is going to equal the total mass of air, so M1 plus M2, which is M total, times the gas constant for air, times final temperature, divided by V. And in this case, V is going to be our total volume. So V is equal to V1 plus V2. Okay, so 1.5 cubic meters plus 1.5 cubic meters. So this is going to be 3 cubic meters. All right, so the key here, the piece here we don't know or what the mass of air is on each side of the divider in our box, or on each side of the piston in our box. And so let's come up with expressions for mass. So M1 is going to equal the pressure on the left-hand side of the box times the volume on the left-hand side of the box divided by the gas constant for air divided by the temperature on the left side of the box. M2 is going to be equal to the pressure on the right side of the box times the volume on the right side of the box divided by R times the volume on the right side of the box. And it's really important to get into the habit of expressing everything in terms of variables until the final step. So let's try to clump together some like terms and get rid of the number of variables we're working with. So V1 is going to equal V over 2. And V2 is also going to equal V over 2 if we're just writing it in variable form. And T1 is equal to T2 is equal to TF. So let's rewrite this as M1 is equal to P1 V over 2 over RTF, and M2 is equal to P2 V over 2 divided by RTF. Okay, so now what we're going to do is we're going to sub in M1 and M2 into our equation above for PF. And so PF, final pressure, is going to be equal to P1 times V over 2. And you'll notice that we're dividing by RTF here, and above we're multiplying by RTF. So the RTFs are going to cancel. Okay, and then this is M1 plus M2, so plus P2 times V over 2. And once again, the RTF would have canceled. And then we have to divide by V. And you can see clearly here that the V's are going to cancel, and we end up with PF is equal to P1 plus P2 over 2, which we intuited at the beginning of this problem. And so PF is going to equal 4 bars plus 2 bars divided by 2, which is going to be 3 bar, like we said at the beginning. All right, so our last step now is to look at the entropy production. Okay, so we are working with an isolated system or an insulated box. So we know that this is going to be an adiabatic process. We have no heat exchange between the system and the surroundings. So because it's an adiabatic process, if we look back here, At our entropy balance, delta S is going to equal the integral of del Q over T plus entropy production. Well, for an adiabatic process, this del Q over T term becomes 0, and we just end up with delta S is equal to sigma. So for our entropy balance in this case, delta S is equal to sigma, and that's going to equal delta S on the left side plus delta S on the right side of the box. So the final entropy minus the initial on the left side plus the final entropy minus the initial on the right side. So the entropy produced is going to equal the mass on our left side of the box times our final entropy minus our initial plus our mass on the right side of the box times our final entropy minus the initial on the right side of the box. And so if you remember, a couple lectures ago, we practiced looking up entropy as a property in the tables and how that works a little bit differently for ideal gases. So let's write it out and keep in mind then equation 6.2 or 6.20a from your textbook, which says that delta S for ideal gases is going to be S reference at T2 minus S reference at T1 minus R times the natural log of P2 over P1. Okay, so that's delta S for an ideal gas using the tables. So let's write that out. And so we have M1 times S reference F minus S reference 1 minus R times the natural log of PF minus P1. Okay, so that's this term here, plus M2 times S reference final minus S reference 2 minus R times the natural log of PF over P2. Okay, and so you might have remembered though, or if you just look at this equation, that this S reference in your tables is a function of temperature. And so SF, S reference F minus S reference 1, those are going to be equal to each other because the temperature is 400 Kelvin for each, so that goes to 0. So these become 0 because they're equal. And the same goes for here because temperature is 400 Kelvin for each. And so what we're left with is sigma is equal to M1 times minus R times the natural log of PF minus P1 over P1 plus M2 times minus R times the natural log of PF over P2. So now let's go ahead and sub in our equation for M1 and M2, our expression for M1 and M2 in each case. So sigma is equal to, and I'm going to pull out the minus V over 2 TF, and there was also an R in there, so the R will cancel with that R, times P1 times the natural log of PF over P1 plus M2, actually, plus, didn't mean to put the bracket there. Okay, so if we just go back for a second, we see that M2 is equal to P2 V2 over R T2, and V1 equals V2, T2 equals T1. So that's the TF, and that V is there. And so now we just need our P2 times the natural log of PF over P2. All right, and so then we just need to plug in our values. And so we get minus 3 meters cubed divided by 2 times 400 Kelvin times P1, which was 4 bar, times the natural log of PF, which was 3 over P1, which was 4, plus P2, which was 2 bar, times the natural log of PF, which is 3 over P2, which is 2. And then this is going to be bars, and we're going to have, so that's bar, but we have 100 kPa per bar. And so then the bars cancel, and kPa's times meters cubed give us kilojoules, and so we have kilojoules per Kelvin, which is what we want, which we end up with 0.1274 kilojoules per Kelvin for entropy production. Positive entropy production, that makes sense. And that is it for that problem. And so we're going to do some more practice with this next time, and we're going to start applying the second law to control volume problems. So I will see you then. Take care.